Hello, I'm Logan Bailey's, and today I'll be covering Chapter 21.6, Gauss's Law and Conductors. We'll be starting off with solid conductors and electric fields. Here we have a solid piece of conductive material. It will begin before it reaches this stage as net neutral. The particles will be equally distributed randomly throughout with no sense of order, but at the end of the day, neutral before it enters the uniform field that I've designated with these yellow lines. The conductor will internally, upon entering this field, create a field in response to the electric force of the uniform field it has been placed into. So the force of these field lines upon these particles will organize them in a way that the negatively charged particles will align themselves with where the uniform field lines enter your conductor, and the positively charged ones will align themselves where the uniform field is exiting throughout. This will create a field inside of your conductor that will cancel out once it's finished reaching its final phase, where the particles within the conductor align with the uniform lines and in turn reduce the electric force to zero. Since it takes force to move these particles around, once they've reached a place where they can't go anywhere anymore, again, they have nowhere to go. No more force is being acted upon them. They aren't accelerating. Thus, at this moment, it will be treated as electrostatic equilibrium, is what that phase is known as. We'll move on to charge conductors. Here you have a hollow spherical shell of, again, metal, conductive metal. It will be net neutral at the beginning. You will then place a large amount of positive particles within this sphere, within the hollow part, closed off in a tight area. Well, Coulomb's law dictates that these like charges will repel from each other, that they will try to expand in whatever way to get as far away from each other as possible, so they'll be heading towards the surface. Well, as they leave the center, and as all of them approach the surface to get as far away from each other as possible, this will leave the conductor in electrostatic equilibrium in the center. So the interior is neutral. Well, alternatively, it gives way to a surface charge. The charge is only located along the surface at this point, which moves us on to this next picture where your electric field lines are coming through the surface, away from it since it's positively charged, and they're only along the surface. There's nothing inside. There's no more charge or net charge, and there's no more field lines. So the flux within the purple Gaussian surface will equal 0 because flux is equal to E times A cosine theta, and if there's no E, there's no flux. Alternatively, flux within the orange Gaussian surface will be equal to the surface charge density multiplied by the area divided by epsilon naught. Since charge is distributed equally, it is assumed that the field lines out of the sphere, away from the surface, will be perpendicular with the Gaussian surface. Thus, your cosine is non-existent in this equation. Furthermore, if you cut a tiny piece away, which you could call dA or A or whatever you'd like, it will be an extremely small slice of conductor, so small that it is flat and the field lines become orthogonal, perpendicular with that surface. Thus, the cosine again is equal to 1, and you can get the cleanest answer possible. Here, your Q enclosed, the total amount of area enclosed, or whatever Gaussian area you want, which here it's dictated by dA, so it's this, just scaled up. It will be equal to the surface charge density of this whole thing multiplied by whatever area you're being given. So your flux, again, is equal to E multiplied by dA or A. They're interchangeable. Which is also, flux is equal to Q enclosed divided by epsilon naught. Well, Q enclosed is equal to the surface charge density multiplied by your area. So that is also equal to the surface charge density multiplied by A divided by epsilon naught. Again, here's just another statement about how A is a placeholder and it can be replaced with dA. Taking that a step further, we reach infinite plates of charge. So you have that plate once again, and it is stretching in all directions in an infinite way. But now, instead of it only coming out of one side, the outer surface of the shell, it is coming through both directions. So there's an equal amount of charge coming from the front and from the back. Well, the fact that the total field coming from a charged conductor leads to the assumption that the total field is still equal to the surface charge density divided by epsilon naught. No matter what, it will still be equal to that because that is the total charge of a conductive surface. After shifting around the equation on the previous slide for E, as you can see here, if you take this equation and you substitute A back in for dA, the A's cancel here, and you get E is equal to surface charge density divided by epsilon naught, which is what we have right here. However, since the field is now coming from two sides instead of one, and that value of both sides combined is still equal to this here, the surface charge density divided by epsilon naught, each side now produces half of the whole field. Thus, the field generated from one side of a mirrored infinite plate charge is equal to the surface charge density divided by 2 epsilon naught. This is represented pretty well in exercise 21.28 on homework 2. Question being, what surface charge density on an infinite sheet will produce an electric field of 1.4 kilonewtons per coulomb? Relatively same drawing. I wrote out 1.4 kilonewtons for your E value can be stretched into 1.4 times 10 to the third newtons per coulomb. But again, you use that equation because it only wants one side. For this example, we used red, which is why I wrote red here. E is equal to the surface charge density divided by 2 epsilon naught. Well, you rearrange to solve for the surface charge density as it asks, and so you get 2E multiplied by epsilon naught is equal to the surface charge density. So 2 multiplied by your E value, 1.4 times 10 to the third, multiplied again by your epsilon naught value of 8.85 times 10 to the negative 12th, and you get 2.478 multiplied by 10 to the negative 8th coulombs per meter squared. If you want to get the total charge altogether, you'll multiply that value by 2, and if you want to just get the blue, the value is the exact same. Again, they're both equal, and the amount of electric field is passing through them, or again, also the surface density. For a further example, we have book example 21.66 on page 413, where the question is, a point charge Q is at the center of a spherical shell of radius r, carrying charge 2Q spread uniformly over its surface. Write expressions for the electric field strength at A, 1/2 r, and B, 2r. Notice that it doesn't say it is a conductive surface. Thus, since it's not a conductive surface, you will have charge still within the circle, within the shell, the spherical shell, rather than having it all located along the surface. If it was conductive, there would be nothing in here. So for part A, we have to treat this yellow line as the radius of our Gaussian sphere, as mentioned here, where you're enclosed. The total amount of enclosed charge within this sphere is just this first red Q. We can then substitute that Q enclosed for Q and then set that equal to your flux equation of Q enclosed over epsilon naught. The Q doesn't really change, it just loses the fact of, it just loses its enclosed nature. We also know that flux is equal to EA, and cosine is 1, or the cosine value is equal to 1 because perpendicular from all directions. A is equal to 4 pi r squared because it's a sphere. You then set r equal to 1/2, which with the 1/2 r squared it becomes 1/4 r squared, and the 4's cancel each other. Set the two equations equal to each other, and you'll get Q, being the charge in the middle, divided by epsilon naught is equal to E multiplied by pi r squared. Well, you want to solve for E, so you have to divide this pi r squared across, and you get E is equal to Q divided by pi r squared epsilon naught. The next one is handled roughly the same, except I highlighted in cyan the parts that are different. But again, this is now 2r instead of half of r for the radius. So this whole sphere is the new enclosed charge, which is red Q plus the 2 blue Q's. So we have a total enclosed charge of 3Q. Here the flux, again, is still total in charge divided by epsilon naught, which is now 3Q divided by epsilon naught. The equation for flux is still the same, with area being 4 pi r squared, because we're still using a sphere as our Gaussian surface. R is equal to 2r, so 2r squared is 4r squared, multiplied by 4 pi is equal to 16 pi r squared. Set them equal to each other. 3Q divided by epsilon naught is equal to E multiplied by 16 pi r squared. And then you divide everything but the E across, and you get E is equal to 3Q divided by 16 pi r squared epsilon naught.